All right. So I think at this stage, I think you've all heard about the concepts of having a real-life digital twin. So what I propose now is to talk about its technical impact on design and analysis in some aspect of manufacturing. So I was asked to just mention a few quick words about me. So I'm Director of Technical Pre-Sales at Maya. So we're mostly focused on simulation. So our team looks at all the multi-physics aspects of simulation, CFD, thermal, structural, new technologies like additive manufacturing. And part of our responsibilities is to work with companies to identify and implement the most value-add solution from a simulation perspective and make sure that they're successful with it. A few fun facts about me. I did a PhD in solid mechanics, focused on multi-physics at MIT. So an MIT alumni. I did work on 2 spacecrafts, which are eventually going to be put in orbit, hopefully. Right now, I think one of the launches is scheduled for June 11th, so unless there's a fatal explosion of the Falcon launcher, it should be set in space. Since we're in the UK, I'm also a big fan of Game of Thrones, but I have not seen the Sunday episode, so no spoilers, please. Jokes aside, let's begin. So the main purpose of this slide is to show you that in engineering, it's important to reuse slides and reuse material. Okay. Actually, that was a pure coincidence here. Well, to cut it short, I mean, we've all read about and witnessed, multiple advancements, right? And making sure we adapt to those advancements can make or break a company. So, this is New York Avenue, 1900. In only 13 years, cars went from a nice to have to an essential part of our life. Right. Same thing again, right? St. Peter's Square. So again, in 2005, that cell phone was probably not, worth it. The quality of the picture, the quality of the video might not be worth it. But in only this time, 8 years, right? This trend still holds, right? And we now have someone with an oversized tablet. But for anyone who has children and who's traveled with them recently, it's pretty darn useful. Okay. So the reason why I wanted to show you this is to emphasize how fast products are evolving. And they're evolving so fast that one has to wonder if we're witnessing something that's similar to the Industrial Revolution of the 1800s, where handcraft went to machine-driven, mechanized factories. And in fact, industries have already started making adjustments for those changes. And this is the so-called digital enterprise or Industry 4.0 that my colleagues have been referring to a lot so far. It is an industry that really focuses on having a very fast-paced, flexible, and holistic approach to design and manufacturing. So you've seen, through the different presentations, how Siemens positioned itself as a leading partner in this digital transformation via the SimCenter portfolio. Now let's take this one step further and ask, what are the trends impacting the different industries, and where can the SimCenter portfolio help play a pivotal role? Okay. So if we look at products, well, they've grown in complexity with the interconnections between mechanical, electrical, and electronics not only being, a nice to have anymore, but mostly being mission critical at this point. Just to put things in perspective, who has a smartphone or an iPhone here, right? Just hold it real quick again. I know it's the second time, but just right now, individually, you do hold more computational power than all NASA had during the Apollo missions in the 1970s, just with that single iPhone or cell phone. Right? So products have grown quite complex. Materials and manufacturing processes are evolving too, right? Just shorter development cycles, growing costs, motivate the needs for new methods like additive manufacturing. Just 3D printing by itself has an estimated economic impact of $550 billion a year by 2025. There's also a paradigm shift from mass production to the more and ever more demanding consumers asking not only for mass customization, right, but also ever more complex products. So, just quick quiz here. How many lines of codes did the first car have, in the past, if any? How many lines of codes does a Tesla 3 has today? They have more than 200 million lines of codes in a single Tesla. And finally, as product grows in complexity, so stricter become the regulations and required certifications, so adding further costs and risks and development time. And examples of these trends are all around us. Just look at your competitors, look at what you're doing. These are everywhere. But since we've talked about moving from horses to cars in less than a century, let's do the thought experiments and choose the electrical vehicle, for example. Okay, so with all the changes happening at the moment, we could very well see the end of the traditional automotive era as we know it. And just to put things in perspective, right now there's about 421 different companies developing EVs and light trucks across the world. So how does one survive, and how does one become a pacer in that environment? And as if the competition was not enough, the cost of entry is also immense. How many different technologies are involved in an EV? Right? How many sensors and microcontrollers does it take to create one? And how many variants of each exist? Right? So how can we test them all and succeed where others don't? In other words, in this environment, how does one become an industry leader? And from a process standpoint, what tools can you leverage to meet the shorter development cycles, the increasing customer expectations, lower costs, and more stringent regulations? So going back to the trends I've just presented, so the 4 key points, let's see where Siemens and Maya can help. And let's take an example where the digital twin was applied in the EV industry. Okay, so when you think of an EV, right, can we think of interconnections between systems? Right, and obviously we can. Right, so one of the fundamental questions, or one of the first question one might ask is, how do I choose my battery cell, my battery pack? In which configuration will I be using them? For instance, so how can you choose the battery when everything else depends on it? And for instance, the final design, that includes the battery, might create heat spots or thermal spots that might generate thermal runaways from the battery, or increase the pace of material degradation that will require eventually a redesign of the battery pack or even a revision of the requirements. So the traditional view of CAE is to use CAD geometry or detailed CAD geometry, which is not always available, especially early in the design. So we have what we call system simulation. We instead work with a network of simplified but validated physical components. Those components can be, include classical hydraulics, mechanical, thermal, electrical libraries, but also industry vertical, like lithium-ion batteries libraries. So what that means is that even with limited, even with limited unpublished data, you can quickly run simulations and compare performance of various designs using those built-in libraries or manufacturers' data sheets. So imagine running over 55 different battery configurations, each over 24 hours input mission or mission cycles, and then be able to track battery metrics like the state of charge, like the material degradation, and run all of this in less than 20 minutes. Right? So that's really one of the value add of being able to do system simulation. Now, in the same vein, designing electrical machine without a clear definition of the operating conditions can be a challenge. So right now, 90% of the EVs use what we call permanent magnet electric machines. So those are superb machines, but one of the challenges is that if the operating conditions go beyond a specific temperature or a specific operating point or rated current, that's called the knee point of the magnet, you can get what we call demagnetization. And what that essentially is a permanent loss in efficiency for that magnet, and that's a big no-no, right, for an EV. So to make sure we get it right, we either have to build the motor and test it, or use simulation, right? And simulating it with the right tool will allow you to evaluate multiple designs, test different windings, coils, material configuration, to make it sure you get it the right time around. But then, even when doing so, you're only designing a motor for a specific operating point, right? In reality, the motor is part of a system. And that system dictates those operating conditions and may lead to transient effects, which in turn lead to degradation or demagnetization of the motor. So our simulation tools allows the coupling of both electromagnetic tools and system simulation tool to be able to capture those transient effects and capture those nonlinearities. Okay. And this is a classic example where we're trying to determine the optimal motor topology to maximize the performance at different loading points while minimizing what we call the cogging torque. So essentially the torque it takes to move the shaft by hand at zero current. So the traditional approach would be to change the parameters manually using a typical design of experiments. I'm sure all of you guys have heard of this before. But it's time consuming, and then you have to visually inspect and pick the design. So sometimes even with simulation, it could still be difficult to these kinds of workflows. And like Joe mentioned, we have what we can accomplish with a tool is a fully automated design exploration. That's easy to use by non-experts, that's fast, and that connects to over 50 different engineering tools, Siemens or non-Siemens alike. So in this case, where you're using our motor simulation tool with system simulation, we're also connecting it to Excel and some CAD tools to generate that CAD. And all of this is possible using what we call the Sherpa technology, which was acquired by Siemens not too long ago, and is a technology that was developed by the same professor, or in partnership with the same professor, that invented the genetic algorithm. So Professor Deb from Michigan State University. Okay. So in this case, we're running over 200 different motor configuration, obtaining the geometry on the fly, the motor efficiency map, average efficiency, and also its cost. Okay. How about product customization and associated challenges? So as we've been mentioning, designs are evolving constantly. Think about the size of cell phones then and look at yours today, right? So those changes not only affect the CAD designer, but it also affects the CA analyst that needs to make sure that the product you're developing is structurally sound. Right? It's like always a conflict between, let's say, building engineers and architects, for instance. And one of the recurring questions when it comes to using simulation to validate the behavior is my model an accurate representation of the physical reality? Right? Because assumptions are made when using simulation. How can we validate those assumptions? And also maybe another question is, what if we don't validate those assumptions, right? This is, not sure if you guys have heard about that bridge in Washington, D.C. It's the Tacoma Bridge, very traditional, which was designed without validating its behavior for aeroelastic flutter analysis. Okay. So that's, of course, a worst case. By the way, that bridge was built and then fell after 4 months. Just to close the story here. So for designs like a car frame, if we go back to our EV industry, getting the answer to this is typically accomplished using experiments. So what we do is we put the accelerometers on the structure and compare the modal content or the modal assurance criterion or MAC value. And then we'd realize that the experiments don't exactly match our simulation model. So we'd go back to the test bench. We'd add more accelerometers to increase the quality of the data and then modify our simulation model, and etc. So this is really an iterative process, and there's a lot of time involved. It's difficult. So with our solution, what we can do is automatically correlate, update, and align our model with the test data, making sure that it is accurate, the first time around. On the other hand, from an experimental perspective, another challenge is where should I put my accelerometers on the structure, or where should I excite the structure to make sure that I maximize the quantity and the quality of that data from experiments. In an ideal world, what we do is we put an infinite number of accelerometers on the structure, but the reality is those accelerometers, takes time to install, they're expensive, and also there's a test equipment limitation to it. So how can we shorten this process and reduce the time spent on capturing that data, right? Uh, Again, with our tools, we can accomplish this. We can accomplish something that we call pre-testing that helps you identify a priori, so before actually doing the experiments, the location that would maximize the value of each test using algorithms. Some of them you might know, so normal mode indication of function, so NMIF, which is one we typically use. So with this, we now have an accurate representation of our reality through our model. Now back to our original question, right? Is the product that we've designed, the new product, is it structurally sound? And how long will it last? How can we quantify this? So we can do this using the concepts of durability, so the science behind durability. And our durability solution, is aimed at answering questions like, will my model crack, right? Will my product crack? Where will it crack? Will the welds last, and for how long, right? So where are the critical areas that I need to reinforce to avoid massive failures, like the one that happened with the Liberty ship during World War II, where you had just straight welds throughout the deck. Or like the Boeing 737 was on its direction to Hawaii, where the engineers did not take into account the cycling for pressurization and depressurization, which led to a durability failure in the explosion of the cabin. So admittedly, there are many ingredients to a good durability analysis, but a crucial part is also to get real-life operating conditions. And again, Siemens and Maya, in the spirit of having an holistic workflow, we have a dedicated data acquisition platform as well that permits this natural exchange between data collection from a low perspective to simulation. So there's a direct pipeline workflow between the two to accurately predict failure. And what can you accomplish with this data in hand? Well, just for a few examples, you can predict maintenance predict maintenance schedule, tailor product warranties, lightweight your parts, but also meet the new and fashionable regulations. And speaking of which, regulations, right? This comes as no surprises. The more complex design becomes, the more technologies are involved in each product, and therefore the higher the odds of failure, if one might say so. And the holy grail being the 5-9 rules, reliability, 99.999% rule. And this is particularly true for electronics. It is the foundation of so many things: controls, automation, performance, safety, and we've seen some of that recently in the aerospace lately. Their performance and reliability is affected by multiple environmental factors, and probably one of the most important one is their operating temperatures. High temperatures decrease product life, decreases efficiency, increases system failures. However, if the product is too cold, well, I bet someone somewhere will ask you, why are you not pushing it to its limit? Why are you not increasing the power density in it, right? If there's such a margin on it. And these conflicting problems always drives a continuous push for better and better thermal management systems. And again, we can do it experimentally, or we can do it using simulation tools, like we saw just up there. Another challenge in electronics design and simulation is the sometimes disconnected world between ECAD and NEPCAD engineers. Each of them working with different tools, different models. ECAD will look at things like layouts and schematics using tools like Mentor Expedition, which is, as Joe and Stephen mentioned, now part of the Siemens ecosystem, while MCAD engineers will run structural analysis for fatigue. We'll look at CFD, thermal, and so on. And a solution that a CFD engineer comes up with, like moving a position of a component, might make no sense from an electrical standpoint. So to avoid these dead-end situations, it is important to have a seamless collaboration between those two groups and make sure that they understand the need to communicate realistic changes, like keep and keep out regions, vias, etc. And this is possible using the digital solution. So computational fluid dynamics, right? So one of the traditional view of CFD is to do aerodynamics, right? But apart from designing, fast F1 cars for the Red Bull, the Williams, the Ferrari of this world, by reducing drag, what else can you do with CFD? And just going back to our electronic example up there, CFD is accomplished. Thermal analysis can be accomplished, using CFD, right? So to calculate forced convection, natural convection, calculate radiation, validate heat sinks, design new cooling systems using multi-phase flow, and so on. From a macro level as well, being able to accurately capture CFD is also useful. It can be used for instance, to significantly save on fuel consumption by meeting new green standards and regulations, and also ensure maximum human comfort. So in the building industry, for instance, the standards like ASHRAE 55 are designed to put a limit on the allowable felt temperature for human, and also quantify or qualify the quality of the air that they breathe. And that's also applicable in the transportation industry for cars, for airplanes, and trains, etc. And so these standards are gradually incorporating CFD as part of the certification process. And the reason why gradually, I'd say that a typical challenge is that a lot of people, when they hear CFD, they think it's complicated, right? They think about the mesh. How do I tailor my mesh size? How do I choose the right turbulent model? But CFD is evolving fast, and it's changed a lot over the years. And now, what Maya and Siemens can offer is a solution that's tailored to the business reality, right? So either it is to enable tools for designers to do quick validation analysis on their geometry, to running cutting-edge multiphysics simulation for medical devices that requires spot-on accuracy, all the way to coupled multiphysics like FSI, like fluid structure interaction, for acoustics of passenger comfort, for instance. Okay. And speaking of comfort, right, of acoustic comfort, let me just try not to break everybody's eardrums, but let me try to play this here for a moment. So, anyone know what car this is? That's a Daytona Charger, very popular in the United States, especially. Let me play another one here. Oops. Well, the point of it is you can typically hear pretty much nothing, right? Because the sound was from a Tesla 3, an electrical vehicle. Okay, that's the point.
It's quite comfortable.
It's quite comfortable, right? So just to show of hands here, who preferred the Daytona noise if they were driving? Okay, let's say a third of the room. How about who better likes the Tesla sound or the electrical vehicle sound? Very quiet and steady.
The low range.
Okay, well there's two crowds here, definitely. So the idea here, I want to highlight is how can you design in order to be in that acoustic sweet spot for your target audience, right? Some people like the muscle cars, other people like me like something that's really quiet. So to do so, we need to be able to understand what contributes to the sound pressure levels and how it propagates throughout the systems. Noise can come from electrical motors, they can come from engine vibration, turbulent winds, but also vibration of the structure itself, like the window panes. And again, for each of these contributions, what is their respective level of impact on the total noise in the end. And again, in this field, we can provide a holistic workflow. So we also, with our simulation portfolio, we allow a simulation of acoustics, vibroacoustics, so the effect of the vibration of the structure on the fluid, aeroacoustics, so the effect of the transient turbulent oscillations in the wake. And this is accomplished using state-of-the-art algorithms that allows assembly-level acoustics. So imagine doing the NVH or noise vibration architecture analysis on a whole vehicle. This is possible using our solution. And again, just to close the loop, we also provide this video should have played a while ago, apologies. We also provide data acquisition equipment to visually validate and assess sound quality characteristics and their location. So we have a piece of equipment that's called a sound camera, which is literally a point and shoot and gives you a picture of the sound and their pressure level spectra. And naturally, both the experiments and the simulation tools are designed to work together and allow a seamless communication of the data from platform to platform. Okay. So why data management? So far, we've seen throughout the presentation that products increasingly involve multiple engineering disciplines and therefore require communication of more and more unconnected data. And with the digital industry or the Industry 4.0, they rely increasingly on simulation, which generates a new type of data, right? So simulation data. So the question is, how can you get control over your CAE data to address the ever-shifting regulations, standards, moving objectives, and keep track of all the different product variants? So our engineering data management platform is designed to do just this. It's designed to give you power over data and give you benefit across all levels. From a user standpoint, what we've seen, this is a study I think that was done by, I can't recall the company that made the survey, but that in most companies, about 30% of the analyst time is spent on looking for data. Just where's my model? Where's that version? I have a set of results. Which design is it related to? Right? How can I pull up that model and run it again and see if I get the same thing? So with the platform and data management, the individual user can deliver results much faster by having all that simulation data all synced with all the engineering teams. And then the teams can make faster and better and more insightful decisions on products as a consequence of having all that simulation data earlier in the design process and also at the tip of their hand. Okay, last but not least, manufacturing is changing. New materials and methods like additive manufacturing are pushing the boundaries of what's possible now. And one of them is additive manufacturing. So as I mentioned earlier in the presentation, the estimated economic impact is about $550 billion a year by 2025. And actually, what's interesting is that more than half tech companies are already using some level of additive manufacturing in their prototyping and already are vesting or reaping off the benefits of that. So this comes as no surprise that the market size for additive manufacturing is growing, but so is the technology. So this is what 3D printing looked like back in the 20th century. So what you see is a supercomputer at the time here driving a 2D printing lithography machine to drive 2D sketches. And this is what it looks like today for plastic parts, of course. I had to limit myself here. So these processes are increasingly used throughout the industry to print standard parts when either the original drawing, CAD models, or tooling equipments are not available, but also to create these next generation organic shapes that you see here. So these shapes are lighter in weight, yet still strong enough to meet performance requirements. And this is where topology optimization come into play. Okay, so it provides the mean to numerically generate those organic shapes as an input for 3D printing machines. And again, in that field, using the Siemens digital solution, designers and engineers can now generate these organic shapes. So on the top left here, what you see is what we call topology optimization. So with that embedded solution, you can easily generate components that satisfies a variety of functional requirements, from structural stiffness or soundness, minimum weight, keep in, keep out regions, assembly constraints, and connection constraints. So topology optimization can be used in the context of an existing assembly. And you can even apply complex structural loadings, like vibration to verify the max von Mises stress, or you look at the minimum natural frequency, for instance, in the aerospace industry. Now, on the right hand corner this time, so a typical problem with most tools on the market right now is the output geometry from a topology optimization is typically what we call a face-set geometry. So it's essentially a one big face, and what that means is that it's very difficult to, if not impossible, to make changes to it or send it to other suppliers to make modifications to it. So the output is essentially a dead end. But that's not the case for us. Okay, so what's unique in our platform is our convergent technology, which allows within a unique CAD environment, so without any export or translation, to edit, combine, or modify that geometry on the fly with traditional BREP surfaces. And what's also exciting about this is that because that geometry now lives in that ecosystem, it's possible to bring it, so to bring that very unique geometry into the simulation world and accomplish multiphysics using our whole portfolio solution. So structural, CFD, electromagnetic, even co-simulation with system simulations and CFD. Okay. And if you still think that modifications need to be done, either on the mesh or in the geometry, you can simply track back the path and go back to the CAD and make those modifications. So that's possible using our platform. And again, within the spirit of a holistic solution, the platform also allows you to simulate the machining itself. Okay, so in the power, the power of the platform not only lies in the process itself, but in its integration in the complete end-to-end workflow within the same environment. Okay. And Siemens is a believer in its own technology. Apologies. So the saying is, they're practicing what they preach. And this is actually from one of the Siemens facility in Worcester, about an hour from here, where they're 3D printing metal parts, and actually more specifically 3D Inconel turbine blades for their gas and power division. So the technology uses powder bed fusion to create metal parts that have properties almost identical to those that you would obtain using typical processes like forging or casting. So this is an example. So we have the tools to generate the numerical CAD topology, and we have also the printing machines and the infrastructure to create those parts themselves, right? But again, the question here, can we close the loop again and simulate the 3D printing process itself for the additive manufacturing world? And the answer is yes. But one of the questions you guys might ask is, why is this important? Why do we need to simulate the 3D printing process? So during the 3D printing, as the layers builds up, there are what we call residual heat stresses that accumulates over the printing process. And that causes various problems inside the printer, from a distortion of the mechanical properties, so structural issues within the part itself, or simply that you'll end up having a shape that's just too distorted from the part that you actually wanted to print because of the residual thermoelastic distortions. So what that means is that getting it right the first time is almost impossible unless you have years of experience, or if you simulate it to make the predictive adjustments beforehand. So not only will this save you time, but also been shown that additive manufacturing simulation as a result can help reduce material by up to 65%. So material waste by 65%. So in this example here, our simulation tool allows you to build everything from the build trays, the support structure, input the properties for the powder to simulate the powder bed fusion process. And then the holy grail of the simulation is to be able to do model compensation. So let's print a part that's a little bit distorted from the get-go, or that deviates a little bit from the original geometry, so that the final part after residual distortion is exactly what you want. So that can be done in an automatic fashion. Okay, so that was quick. You've seen how each module in the portfolio can give you a competitive edge, whether it is for better efficiency, faster production, or lower costs. And the idea beyond all of this is to emphasize that the impact of having a digital twin is exponential when you have a well-thought workflow, but also when you have the right tools to accomplish the task. So just a heads up, thank you all for your attention. This afternoon, I will be having a deep dive session or technical session. We'll jump into the software, show you kind of what they look like and some applications we can do for a few of the tools that I've presented today.